Hi all, hope all is well. On today's video, I wanted to do a test on a couple of the components that I have been creating from my electrolysis unit. So, as you can see over here, the electrolysis unit is set up using solar power. So it goes back to a battery bank, back to the solar panel on the roof. And the electrolysis unit is processing seawater into sodium hydroxide in what's known as the cathode, and chlorine in the anode itself. So it's just breaking down the salts in the seawater through the process of electrolysis. So just using electricity as a pair of chemical shears to break apart the ionic salts in the system. In the seawater. So as you can see here, this one is discolored, slightly green, and this one is nice and white, and you can actually see a buildup of material on the bottom there. So what I've been trying to do is create sodium hydroxide over here in the cathode cell itself, and also creating a byproduct of chlorine. I have very little use for chlorine, however I am content in knowing how to manufacture it, but there are ways to improve the shelf life of the chlorine products. There's two ways that I'm familiar with myself, and the reason you want to improve the shelf life is because it disintegrates very quickly, so it will degas and you'll be left with acidic water, but your chlorine product will actually be gone, so all the beneficial stuff will be gone. As for the sodium hydroxide, you can store it as a salt form, so you can actually dehydrate all the water off it, and you could store the sodium hydroxide that's produced through electrolysis as a salt. Now, the salts you may be familiar with. If you've ever manufactured soap, for example, sodium hydroxide is definitely a product you use in soap manufacture. It's also the same product you use to unblock your kitchen sinks and that as well. So sodium hydroxide is really important in the chemical industry, and so is chlorine. Now, what's actually really amazing about this system is if I was to take some of this hypochlorous acid that is forming here, so chlorine mixes with the water solution in the anode cell, producing hypochlorous acid, and then I have an overflow, so I'm finding that it's becoming a chemical pump. So it has ionic transfer, and it's actually pulling the fluid from the cathode into the anode, and it extrudes it out the anode. So you can see some runoff there, some rust marks. It's flowing into this jug here, and then out of the jug through a hose at the bottom here, and I've actually got it collecting in a bottle down here now. So I'm catching the runoff, and that is actually hypochlorous acid and hypochloric acid. So you could actually, in theory, to stabilize that down there, you could do one of two things. One is to leave it in the sun and let the UV take it to the next level, so it actually oxidizes further and potentially creates what's known as perchlorates. And perchlorates are what's used in oxygen candles. And for those who are unsure of what an oxygen candle is, it is a candle that can be burnt to produce copious amounts of oxygen. And they use these oxygen candles in submarines and for space travel as well. So it's for producing oxygen where you normally wouldn't be able to access it. So perchlorates are actually really interesting, and I'd love to go down that pathway at some point. However, it's a little more tedious than what I've made it sound, and I am unfamiliar with exactly the process behind developing it, but it is something I'm willing to have a crack at some stage. But for the time being, what I really want to do is I want to take some of this chlorine solution that I've manufactured here, and I want to stabilize it. And the best way to stabilize it is to add some sodium hydroxide to it. Not a great deal, just a little bit. And with that I should be able to stabilize it from an acid into bleach, or sodium hypochlorite, which is a common household bleach. And the way you test it to see if we've been successful in doing it is to do a test on the chlorine itself as it is, and we should see a red reaction using litmus paper. So I have some litmus paper over here somewhere, and you can see there's a bunch of numbers and colors there. It's very acidic down here, number 1, number 2, and then if you get it up to number 13, 14, it becomes a base, and that's what we're aiming for. We're aiming to transform it from a 1 or a 2 into a 13 or a 14. So that's what this test will all be about. So I've actually got some gear set up over here to have a go at this. It's going to be a bit of an unusual setup, so please bear with me as I have no equipment to actually record this correctly. In here, this is where I'll be doing my mixing, and I'll be using this syringe to draw from the fluid. And I have my chlorine product in here, and I have my sodium product in here as well. So I'll just take the lid off the sodium product first. So this excess fluid that you actually see in here is what I've been collecting from my hydrolysis system for the last couple of weeks. So we're going to, what we might do first is we'll take the lid off both of them. We'll take the lid off this one as well. And that way we can test them with the litmus paper first, so everyone can see for themselves that they are indeed an acid and a base. You can see there's quite a bit of charcoal build up in that bucket there, the chlorine bucket, the hypochlorous bucket. So if we test this, it should be red, as you can see there. So that's positive for very acidic. So we'll leave that there. And if we test the sodium product, it should come up as a green to purple solution. However, it needs to be reduced as well, and I think that's where I'm going to have to take the time to actually reduce this down by applying some heat to it and evaporating it further, which concentrates it into a richer source of sodium hydroxide. Now we want to be careful not to get the bottom dregs as well. So the white material we seen earlier is actually magnesium hydroxide, and we don't need magnesium hydroxide for this reaction. We're only chasing the sodium hydroxide that's in the top fluid. So we'll do a test anyway and we'll have a look. So it's not the most successful test. It has gone green, very light green. So I think I need to concentrate it, which I will do immediately. So what I might do is I'll take this little jar here and I'll take some up to the house and I'll actually boil it in a saucepan. Now, if you're ever doing this at home, you should be aware that make sure if you're boiling it down and reducing the fluid, so removing the water from it and concentrating the sodium hydroxide, that you don't do it in an aluminium pan. If you do sodium hydroxide with aluminium, you can produce hydrogen gas, and hydrogen gas and fire do not mix. At some stage I would like to do some experiments in a safe way, showing people how to produce hydrogen gas and stuff like that, but that will come at a later date. It's not in this video, but it is something you need to be aware of. If you are reducing sodium hydroxide fluid, make sure you reduce it in a stainless steel pan, not in an aluminium pan. Okay, so I managed to reduce this. We got it down a decent way. We've probably removed 9 parts of the water. I think something like that. So we've reduced it to 1/10 of what it was, approximately. And what we need to do now is we need to do another litmus test on it to see if we've concentrated it. And this will determine whether I am actually making quality sodium hydroxide as well. So we'll put this in. And that is not a very positive test, honestly. It's working to an extent, but it's only very weak. I am a little disappointed with this. You're talking maybe an 8, pushing a 9, definitely not a 9, more like 8, which is very disappointing, to be honest.